Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. Today we're revisiting the basic principle of the pressure altimeter and its limitations. We'll also cover altimeter settings and why one is used over another. Let's define some key terms first. Altitude means vertical distance of an aircraft above mean sea level, sometimes called true altitude. Elevation also uses mean sea level as datum but applies to fixed objects like ground or runways. For example, Schiphol Airport has an elevation of -11 feet. Even objects above ground, like a control tower, also have elevation. Runway elevation plus tower height. Height is vertical distance above a fixed datum. An aircraft above an airport has a height relative to the airfield elevation. Height can refer to movable objects, like aircraft, or fixed ones, like a mast. A mast can be described by both its height above ground and its elevation above sea level. Next is flight level, also called pressure altitude. It's the pressure difference from a datum of 1,013 hectopascals, converted into feet using ISA. Under ISA, flight levels equal true altitude, but in real weather, temperature variations mean flight level differs from actual altitude. Now let's recall altimeter principle. At 1013 hectopascals at sea level, pressures at higher altitudes are predictable. 10,000 feet is approximately 700 hectopascals. 20,000 feet is approximately 450 hectopascals. 30,000 feet is approximately 300 hectopascals. But this is only true in ISA conditions. Real level pressure often ranges 950 to 1,050 hectopascals, rarely exactly 1013. If sea level pressure is different, the whole pressure profile shifts up or down. If we don't reset our altimeter, we introduce barometric error. Example, if airport elevation is at sea level and actual sea level pressure is 995 hectopascals, we must set it correctly. Otherwise, the altimeter will be wrong. Now suppose pressure is standard but temperature is different. Warm air expands, spacing pressure levels farther apart. Cold air compresses them closer. This creates temperature error. The altimeter may overread in cold air or underread in warm. This cannot be corrected directly on the instrument. Instead, pilots use calculations or tables to apply correction. If not, altitude indicated may be dangerously inaccurate. Close to the ground, errors matter most. Pilots must set the altimeter to the correct sea level pressure, QNH, and, if needed, apply temperature corrections. At higher levels, safety means separation from other aircraft, not terrain. Here, both pilots use 1,013 hectopascals and fly by flight levels. This way, both aircraft share the same pressure datum, so their vertical separation remains correct even if true altitude differs. So we have three common settings: QFE, QNH, and 1013 standard. These Q codes come from Old Morse abbreviations. QFE equals altimeter reads 0 on the ground. It shows aircraft height above touchdown, used in basic flight training. QNH equals altimeter reads airport elevation on the ground. It gives altitude above mean sea level and is standard for airline operations. Standard 1013 equals used for flight levels. Example, FL 175 means fly at 17,500 feet on 1013 hectopascals setting. Why is QFE often used for training? Because it's easier. Circuits are flown at 500, 1,000, 800, and 600 feet. Easy numbers, no conversions needed. But QFE becomes meaningless once leaving the circuit. For navigation and obstacle clearance, QNH must be used. Airline pilots always use QNH. Before descent, they brief themselves using approach charts. These show required altitudes at different points. Example, Munich ILS runway 08 left. Touchdown elevation is 1467 feet. At 12 DME, altitude should be 5,000 feet QNH. At 4.7 DME, 2,680 feet QNH. At the decision altitude, if the runway isn't visible, pilots must go around. For this, QNH ensures safe clearance from obstructions. If QFE were used, they'd need to remember to switch back to QNH during a busy go-around. That's why airlines prefer QNH, fewer distractions. To summarize, QFE equals 0 at runway, used in training. QNH equals airport elevation at touchdown, standard for airlines. 1013 equals flight levels for separation at cruising altitude. That's all for this lesson. We reviewed altimeter principles, ISA assumptions, barometric and temperature errors, and QFE, QNH, and 1013 usage. Stay tuned for the next lesson, where we'll discuss altimeter setting procedures. And don't forget to like, share, and subscribe to StudyKwik.